Oops, sorry about that.
No problem. Another class.
Sorry, Bruce.
Yes.
Can I ask a quick question here? Can you go to the previous slide?
Sure.
Um,
Here we go.
Yeah, sorry, this one. So, why do I see MH is equal to 270 and MH is equal to 135? Do you mean MS is 135?
Yeah, this was before we saw the candidate. This was very early on. So we were basically working with something that was not too heavy, somewhere slightly heavier than the standard model Higgs. And I will give you the story of how we arrived at 150 before we saw the peak at 150. Okay, but everything is driven by the kinematics of the leptons. Based on the kinematics of the leptons, you can infer, you can backtrack the masses of the particles. And I will talk about.
Sorry, the question was, why are there two MH? Although I see the there's two values of M capital H is 270 and 135, although there's just one distribution.
I think there might have been a typo. It's not MH.
Yeah.
I chosen wrong graphs. It's M. The second H is S.
Yeah, that should be MS. So it's exactly half the mass of the heavier H. Okay,
Correct.
good.
Correct. These were very
That makes
early
sense.
studies, but of course,
Sorry.
I will go historically how we progress to get what we have to do.
Okay.
Then there's
and small
another
H
class.
is standard model.
Sorry?
Small H is the standard model like Higgs, so it's 125.
125, yes, 125.
Okay. Okay, good.
So this is one type of multi-lepton excesses. There's another type where since the Yukawa coupling is large enough that you have associated production, double top and single top, and then you basically end up having same sign leptons and 3 leptons, typically with these as well, but not only. Okay, so you basically end up having same sign and opposite sign dileptons and 3 leptons. So it's a very distinct and very different type of signatures. And this is very important because if you see an excess in one type of combinations of leptons, but not elsewhere, you will say probably, okay, this is a statistical fluctuation or a systematic effect. But the fact that we have a comprehensive set of very different excesses, which I will summarize in the table, already starts telling you that this is a much more serious problem. So let's look at the methodology, because when you are searching for new physics, you have to really make sure that you're not hampered by biases or look-elsewhere effects. Because the problem that you have is that the phase space at the Large Hadron Collider is so big that the probability of having a fluctuation from the standard model anywhere in the phase space is huge. You can have a 3, 4, 5 sigmas easy, but there could be statistical fluctuation. This is what we call the look-elsewhere effect, which is not just along one dimension, but it's basically across all the multidimensionality that the phase space of the Large Hadron Collider provides. So clearly you have to get a procedure. Without that, you can't establish an anomaly. So we did this, as already said earlier, based on some features of the round 1 data, the Higgs PT, the HH, the TTH, the BB in round 1. We formulated a simplified model that we thought would describe these. And then this model, the 2HDM plus S, would predict multi-lepton excesses, okay, which were not originally used to define the model, but is a result of the model. Okay, it's a direct prediction from the model. We saw them in run 1 and very, very little run 2 data in 2017. So we published another paper and said, okay, we've seen this multi-lepton anomalies. We've seen these excesses, which at the time were not very strong, but they were already serious enough. And we say, okay, we don't want to do any more tuning or any more changes to the model or the parameters of the model. We're going to fix everything. And now we're going to look into more data or final states that are predicted with the same parameters, because you don't want to basically fall into the trap of changing parameters, and then you create biases and you can get false positives. So back in 2017, remember, this is almost 5 years ago, we decided to say, okay, wrong or right, let's fix the 2HDM process to having the mass of the scalar 270, the mass, the heavy scalar, the singlet at 150, and I will explain why it was 150, and the S is treated like SM Higgs-like, so it will be decaying mostly into WW. Okay, so then we say, okay, whatever, this is probably wrong anyway, this is probably not fundamental, but we're going to fix the model because we don't want to fall into the trap of Lucas wave effects. And then you go to the right part of the slide, where you basically see a bunch of publications. There's more now in the pipeline, where we basically say, okay, now we look with more data or final states that are predicted by the model on the left. But now everything is fixed. So there's no tuning, no scanning, no Lucas wave effect. That's assumed. So whatever we see is basically the result of look there and see what happens, as opposed to scanning. So we now don't scan anymore. We basically say, look there in the mass range as specified by the model, in with the corresponding number of objects as specified with the model, and tell me what you see. That's basically a prediction now, okay? And you see basically all these axes, which we, now all our papers get published. So that already speaks to the fact that there is something happening. And this is a selection, there's of course more papers. So what you do is you basically make a simple assumption, simple answers that I described before. You have a scalar around 270, we actually fixed it. The mass of the singlet at 150, we don't change anything. And then we look at the data. And then what we saw in 2019, this was published in JHEP, is that you have a comprehensive set of excesses that I will summarize in a minute. They're all self-consistent within 2 sigma with a very simplified model with 1 degree of freedom. Back in 2019, the corresponding excess was 8 sigma, obviously way outside the 5 sigma range, but it has been growing. And that's really what's very exciting, that this doesn't go away. It keeps growing and embracing new types of excesses, which we have published afterwards, and we are now also about to publish some more. So this is, I mean, to say that the LHC, there's no new physics at the LHC is fundamentally incorrect. We have to understand this multi-lepton excesses before we can conclude such a thing. And I think now we are fairly confident that this statement is correct. And to say that there's no new physics at the LHC, there's no evidence for that at the moment. We have to understand this. If we don't understand this, that means we are not doing our job in understanding the LHC data. And this is already no longer in a statistical fluctuation. Okay. Now, just to give an example of excesses that even became after we came up with the original paper with the 8 sigma. You can see here, for instance, the invariant mass of 2 leptons with 1b. And you can see the fact that systematic effects, theory related contributions, not even the toponium, can explain this kind of things. And very importantly, the mass of S is sensitive to the invariant mass, is sensitive to, okay, let me turn that around. The invariant mass of E mu is sensitive to the mass of S. That's why we fix it to 150. Because the data run 1 already was telling us that S couldn't be very heavy, very close to the Higgs boson. We fixed it at 150, okay? And we have a full glory of next to linear corrections, next to linear in QCD, next to linear in electronic corrections, and all sorts of extremely amazing progress in Monte Carlos. Another type of excess here, this is with a full jet veto. This is basically the one that I've shown before, is basically with a B-jet, okay? To illustrate that this is not a problem with the top cross-section, you apply full jet veto to look at the non-resonant WW production, and the excess appears there in run 1 and run 2, also given sensitivity to the mass. And when we made an analysis with run 1 data back in 2017, the best mass was 150. That's where the mass of S comes. It comes from the data. It's not made up. And in run 2, we've seen also all these problems of the experiments, especially here Atlas with the full glory of all the quantum corrections, unable to describe the data at low masses, okay? This is a corner of the phase space where the QCD and electronic corrections are very well understood. This is not contrived regions of the phase space, and experimentally, there's nothing more robust than that, Okay. Another type of excesses that I've already described, the opposite sign and 3 leptons, is the fact that experiments are unable to describe the TTW cross-section with the standard model, and also the TTW plus and TTW minus asymmetry. And you basically see that this is one of the excesses that we predicted. This was published in Physics Letters a while ago. Where you basically see that as a part of this ensemble of excesses, you have to see these things going, this excess is going on. The good news is that CMS just came out a few weeks ago with another measurement of TTW. Again, the cross-section is elevated, and the asymmetry of TTW plus and TTW minus is consistent with something like this. So let me summarize, because I only have a fraction of an hour to go through all these anomalies. So what I do typically in seminars is to basically put this table with the type of anomalies that we're talking about that can be described with these simplified model and the significance that we have. So we have a class of anomalies that are basically, they show up as opposite sign leptons mu with jets and b jets. The invariant mass is less than 100, and the dominant standard model process is TT bar. There we have way more than 5 sigma. It also shows up with a full jet veto. The significance there is about 3 sigma. Again, this is unbiased and without Lucas-Ware effect. So this is basically the result of look there and see what happens. It's not a scan, okay? Then we have also same sign leptons and 3 leptons with moderate HT, which is dominated by TTW and 4 top. There is more than 3 sigma now. There is the same, but without B jets, where the measurement of the WH and the triple W are dominant. There we have more than 4 sigma, and this is one of the emerging excesses in the Higgs sector right now. And very importantly, and we're writing a paper about it, is the fact that also the ZW cross-section is also of inserted corners of the phase space as predicted. In fact, the significance is much more than 3 sigma. We put there 3 sigma because we haven't yet fully analyzed a much bigger excess that has been reported by the CMS experiment. So now, obviously, since excesses are continuously being reported, this picture will keep evolving as well. All right, so let me quickly go through the impact on Higgs physics, because we're working very hard to substantiate the plus-minus machine, and the Higgs measurement, in particular the measurement of the Higgs in association with the W, is affected at more than a 4 sigma, more than a 4 sigma effect. And this is extremely important, meaning that the plus-minus machine has to come in to set the record straight as to what is the real coupling of the Higgs boson to standard model particles. It's not just about achieving more sensitivity to the couplings, it's about establishing now there's something happening there at the LHC. So what basically happens in the same model, again, we don't tune anything. We have changed a bit the masses to give you a feeling of the sensitivity, but we again fix everything. Okay, so what we say, we fix the model, now look at the WH measurement. Is it discrepant or not? Because we predict a discrepancy. And then basically what happens is that with this ansatz, with this model, you basically end up having an intermediate boost of the final state. Whereas in the standard model, because there's WH production, you do have a serious boost. This is in red. So the transverse momentum of the decay of the Higgs is much higher. So basically what we do is we concentrate on the measurements of the WH cross-section where you don't go into the boosted regime. If you're in the boosted regime, you don't see a signal in the BSM. You will only see the standard model, which is what we see really. The boosted analyses are consistent with the standard model. The ones that are not boosted are inconsistent with the standard model. And then we did a scan. It took, we had a very thorough review, I have to admit, by the European Physics Journal. And we basically found that back in 2021, that the discrepancy of the measurement of the WH cross-section, which is in terms of the standard model 2.41, which is 2.4 times the standard model, with a significance of 3.8 sigma at the time, was already significant enough, and there was no Lucas-Ware effect. This is a global excess, which is quite large. The good news is that since that paper came up, CMS came up with a new set of results where you can clearly see black and white. You see that for the measurement of the WH and ZH cross sections, but it's dominated by WH. When the PT of the boson is not very high, less than 150, is discrepant with the standard model. So the blue is the measurement, the red is the standard model, and yes, and that basically adds to it. Also, CMS came up a few months back with a measurement of the Z gamma in the WH beam. This discrepancy is 2 point something sigma, the one here is 3.2 sigma, with a huge fluctuation up. This is clearly an upward fluctuation, but it's already telling you that something is happening there with an amazing Z gamma peak with 2 jets, consistent with the WH hypothesis. And last but by far not least, you can see an excess here at 150. Okay. If you put everything together now, the excesses is now 4.2, 4.3 sigma in the Higgs.
Sorry, excuse me.
Yes.
Can I ask a question? Sorry, here in the slide, you're referring to the bump, no, to that, and
yes.
And what is the red curve? Is the prediction?
Okay. So the red curve is the fit of the Z gamma signal in a beam. The digest 3 beam is designed by CMS to isolate the W Higgs signal.
Okay.
Okay, and they see a signal strength of 12, which of course is an upward fluctuation. I'm not disputing that, but it appears right where we see other excesses. This excess from CMS is basically two same sign leptons and 3 leptons. Okay, in addition to everything else. So the measurement of WH is already off by more than 4 sigma, 4.2 sigma at least so far at the LHC. Again, if somebody says there's nothing at the LHC, well, they can say whatever they want. Okay, I'm not going to go through the connection with astrophysics because I'm running out of time, because I really want to concentrate on the 151 excess. And again, and I will leave sufficient time for discussions. So the very important thing when you look for excesses is to avoid cherry picking. This is extremely dangerous, to basically pick up an excess and combine it with another excess. Okay, whatever model you use and whatever procedures you use has to long predate the search. Okay, remember the motivation for something around 150, which comes, let me go back, from distributions like this. Okay, this is basically where the excess occurs, is something not very heavy, or for instance here you look at the invariant mass of 2 leptons. If you fold that into a mass, it's around about 150. So we already had for years indication that something is happening in that mass region. So we basically always said, look, if you use first principles, of course, there's always a model dependency, because if you go deeper into how the dileptons would emerge, that's model dependent. If you have a 3-level coupling to WW, of course, it's straightforward, but you can have more complicated options, which we have studied and continue to study. So there is a model dependence on the mass, but roughly what the search was set up to be somewhere between the mass of the Higgs and 170, just to incorporate the model dependency of that statement, even though the central value was around 150, assuming SW. And then we said that's fixed, and because we have a final state where that is driven by a scalar H decaying into SH, but most now given the Higgs data, it would be more SS star. So that's the evolution of the model, but that's the data that is telling us, not us assuming. In practice, SS star and SS is really the same, but is important within the model. We said, okay, but let's basically search for gamma gamma and Z gamma decays, with the understanding that we don't see anything in ZZ, which already is forcing us to walk away from the very simple ansatz and do model building with, for instance, heavy neutrinos to avoid the S to WW problem. But that's a separate conversation, and we're writing a paper about it. So what we basically do is we assume that these are diboson signatures. That means that the S would come with something else, being that dijets and leptons. So we reuse the Higgs data that measures all these things. Because the coupling to the standard model of S has to be small, because the standard model of Higgs is close to the standard model, then we remove boosted topologies and the vector boson fusion. So everything is basically predefined, so to say, with the settings of 2017. Otherwise, it's almost, I mean, you can see excesses that will come and will go, and it's not useful to search for excesses unless you have a robust procedure. So we felt that this is robust enough in that the mass ranges, the final states, the associated topologies, and the removal of VBF and boosted topologies predate the search, okay? As already documented in our 2017-2018 papers. All right, so what we do is we basically look at all the available data. This paper is now under review. Obviously, because of its importance, the reviews take long, obviously. And people make a lot of requests, and we are complying with those requests. You basically start seeing a systematic excess of gamma gamma and Z gamma with objects. Being the largest, most surprisingly, with missing energy, reported by Atlas, where CMS still has to report with 3/4 of the run-to data, but we see also excesses with dijets, with B-jets, and we also see an excess in Z gamma. This is combined. Now, I will talk about the issue of the model dependency. This is not combined, assuming that the observation is the truth, which of course is an optimistic statement. We understand that. But you basically clearly see that all these distributions are now all they are colluding to get something around 151.2, 152 or so, again, in the final states that were predicted, okay? These are dibosonic final states with a small impact due to the inclusive distributions, okay? So now what we have done as a request of the reviewers, because the reviewers, okay, you can spend hours arguing back and forth, but they wanted to see the local significance with a model. So you wanted to say, okay, if you assume a model and we give them the model, what is the global significance? The global significance drops to about 4 sigma. Just for this. But of course, if you take the simplified model with all the multi-lepton anomalies, basically the significance goes to the roof. So it, you know, for us, it's basically is sort of yes, it's 4 sigma, but you have 8 sigma elsewhere with the same model. So it's like saying you are way outside 5 sigma. So anyway, I think it's a sociological issue. And so in the new version of the paper, we report 4 sigma using a model. So now there is a model, which is basically the biggest global significance we've ever had after the Higgs boson at the Large Hadron Collider. And the good news, which I'm not reporting here, is the fact that CMS has come up with a WW analysis with a clear axis around the same mass. They cannot describe everything with the standard model anymore. We are in the process of combining this with the dilepton studies. Now, few implications for run 3, and I think run 3, I mean, first of all, run 2 is not fully exploited by any stretch of the imagination. I mean, the run 2 remains largely unexplored in many senses of the word, in that diboson signatures, especially SS, is not even explored at all. People are now looking into SH. This CMS started, Atlas is following suit, but where we see the signal is really the SS star. So you have to walk away from the Higgs boson, let me put it this way, to start seeing something. And an illustration of with basic assumptions of the H resonance into SS star, where S would go into gamma gamma and S star into BB bar, is illustrated here on the lower left for the one experiment, the entire run 2 and run 3, assuming 500 femtobars. You could see there basically the red is the background, and the blue will be the signal. That is in the gamma gamma, where gamma gamma is on shell, and the BB bar is off shell. Now in the reverse situation, where you have the BB bar on shell and the gamma gamma off shell, the background is much bigger, and obviously the significance less, but everything counts. It would basically certainly be one experiment, run 2 or run 3, would have a sufficient data to take this signal to the mother, which is the H. Okay, of course, the gamma gamma and Z gamma searches have to be completed with run 2, and a lot hasn't been done. I mean, whatever we have used is only a part of what the experiments have, and hopefully the experiments will do a dedicated study at around 150. But we feel that not only there is something in the data, but it's motivated. So it's not like we scanned the phase space and we bumped into a bump. It's because there were these multi-lepton anomalies that pointed to something at 150, and then we looked at it, which is extremely different, and that needs to be appreciated. Now, actually, over the years, I don't know if those that have been following this, there's been quite some discussion about the 96 or 98 GeV state. And you saw this excess here, very small excess, of course. I mean, you cannot say too much with that. But then all of a sudden, CMS, this is the excess around 2-ish sigma of all the 4-lepton experiments with the standard model Higgs-like couplings. Doing the same thing, CMS came up with an excess here. You can see in the limit, the observation being above the 2 sigma band, searching for an SM-like Higgs. And Atlas, that's not excluded. So, you know, this is very interesting. And there are reasons why I think this actually maybe, you know, years ago I wasn't too hot about it, but now I'm getting more and more excited because this is a source of B jets that we wanted to have. And the adding of this state helps with the WW problem that I alluded earlier, the fact that we have a gamma gamma Z gamma axis, but we don't see ZZ, which basically tells you that the mixing is much more complicated. It's not just the trivial mixing of S with the standard model. So it's a little bit more convoluted. There's something more in addition. So we are basically paying a lot more attention to this, and we're doing model building with the 150 and the 96 as well to make more predictions. I should also point you that last year we had a workshop with about 570 people, with top people. We had the opening of the workshop with Nima and all that, and then we wrote a white paper, and is about to be accepted by the EPJC. And this white paper basically sets up there's a train of thought that we follow to address the issue of anomalies, the complexity of these anomalies, the richness of the anomalies, including the multi-leptons, and the methodological aspects of how we take that forward to really see resonances at the LHC. And we're basically, because the field is at the crossroads, we have a lot of anomalies now. That we have more anomalies now than when we wrote this paper. But now we really have to think very carefully about how to look for new physics, how the experimentalists should look for new physics, how to minimize the model dependencies, how do we walk away gradually from the classical way of searching for new physics, where you pick a model, you optimize a Monte Carlo, and then you design cuts, and then you open the box. That's not efficient. You would need tens of thousands of students to cover everything. We need to be more efficient and be driven by these anomalies more than we are. So I welcome you to take a look at it. And this summarizes not just the LHC, but also all the anomalies in particular physics. Okay, let me conclude. I think that will leave us 10 or 15 minutes for discussion. So the first part of the talk, I basically tried to convince you that there is a major issue of the LHC with multi-lepton excesses. They appear in corners of the phase space where quantum corrections are well understood, and where there is a litany of processes that dominate. Some corners are dominated by WT and TT bar, some for top, some by DV, some by TTB, some by WH, some by WW. So there's no one process that dominates. So we can solve this problem by tweaking a TT bar Monte Carlo, because then you basically leave the other excesses unchanged. This is certainly something way, way, way more complicated that seems to be pointing to something way more interesting than just mismodel. The fact of the matter is that the Monte Carlo community has been aware of this for years, and there hasn't been a single successful attempt to explain, not for the lack of trying, because there's been papers in the literature. Now, if you, one of the important things when you see excesses, once you establish that are not statistical fluctuations, and these are not, once you establish that you don't have Lucas wave effect, that has been avoided here, you really want to understand whether they are self-consistent. Because otherwise you deal with the spurious systems, and you basically, it's very difficult to model or make predictions with it. But luckily enough, these multi-lepton anomalies are consistent with something very simple, which is a scalar which is not too heavy, around the electroweak scale, decaying into dibosons. That's what seems to be in one blow explaining all these excesses. And from the dilepton invariant mass, you can infer that S is not heavy, is slightly heavier than the standard model Higgs. And by doing a predefined search, again, this is not a scan, but a predefined search where we set the rules of this search back in 2017 and 2018, with the data that was taken after and reported after, we've seen something which has a large global excess, at least 4 sigma, which will be, of course, complemented with recent results from CMS. We see also a serious impact in the measurement of the WH as predicted. And this further motivates the experiments to look at, to set up searches specifically for this. That obviously means work. I'm not saying this comes for free, but there's a lot of stuff that comes from the Higgs that could be recycled, and further motivates with run 3. That's for run 2. That will be the 151. There's sufficient data to establish that there's something in the data around 150. The mother of that S, the decay, the particle from which the decay comes, the H would probably need run 2 and run 3. And this can be done also through diboson searches. And to me, I think run 3 is terribly exciting. I think we do have something in our hands. And in light of everything else that's going on in the field and all these other anomalies, we certainly have to be very serious about finding new physics with the new data and being creative in the way we do analysis. Thank you very much.
Thanks a lot, Bruce, for such a nice summary of all the anomalies. Well, probably not all the anomalies, but many anomalies, as you said, there are more coming up. So we can take questions from the participants now, if anybody has any questions.
I would like to ask, so if these anomalies can already point towards some new scenario, like, I don't know, can they say something about supersymmetry or exclude the supersymmetry, or point towards something else?
Okay. Our approach as experimentalists and phenomenologists is to avoid as much as possible model dependency. So we try to minimize the number of fields and the number of interactions. So I cannot answer that question. I mean, our job was for the past six, 7 years is to establish whether these anomalies were due or not to statistical fluctuations, and whether all this wealth of quantum corrections would be behind some of them, and missing corrections would be behind some of them. And there's been a lot of progress by theorists doing calculations that basically, especially in the electroweak sector and electroweak analog corrections, that tend to indicate that where we see those excesses, the electroweak corrections are very small, as sub% corrections, and they're very accurate. So our job was to basically establish that these are real excesses, not fake excesses, okay? Now, obviously, now that we have the first hints, I would say, or something around 150, obviously things become much more serious because you start seeing something narrow, and we know that there's more to come. Obviously, we take time to analyze and all that. So I cannot answer the question as to what kinds of models would be able to be embedded into this. But what we do is to basically say that these are real excesses, what the anatomy of these excesses are based on the one-dimensional distributions that experiments have provided, and what kind of kinematic range would these excesses be sitting at. That's as far as we can possibly go at the moment. We try to stay away as much as possible from model dependencies, and what we're now doing with some theorists in Switzerland and Germany is to basically try to connect these with overarching, to try to create an overarching picture, because there's many other anomalies in particle physics, not just this. So we really try to understand whether with the least amount of model dependencies, we could make further predictions for further measurements. That's what we're trying to do. But of course, I mean, look, theorists can come in and do as they please. I mean, the papers are there, they can look at it.
Yeah, thanks.
Any other questions? So Bruce, you said the first analysis came the first time they observed this excess around 150 GeV. It was in 2017.
Okay, so the first hints in my mind of something consistent with something around 150 came from the di-lepton data.
When was that?
Because of the invariant mass of the two leptons. So if you have, for instance, S decaying to WW, the invariant mass of the two leptons will be slightly bigger than the standard model Higgs. So given the data, so you can see clearly the discrepancy. It peaks about 50 or so, so it's slightly heavier than the Higgs. So if you do the analysis of that data, you come up with something that is around about 150.
Right. So this data is from 2015-16, and obviously they have collected more data since then. They haven't done a reanalysis of this. That significance hasn't improved or decreased.
Well, okay, we did the significance that we calculated in 2019. That was 8 sigma, but obviously things have grown. So obviously counting sigmas is not an issue anymore. It's about really making more predictions in terms of narrow resonances. So we haven't updated this combination. We don't think it's scientifically interesting. What is scientifically interesting is to establish whether there are more resonances. And the 151 came last year when Atlas and CDMS released some more data. So we are now basically studying also a new class of leptonic excesses, but I'm not going to discuss that now before we come up with a paper. But we have stopped combining because we're far away from 5 sigma. We basically, I mean, the paper that was published in 2019 has basically surpassed the criticism and the test of time. And in that the excesses have not gone away and have grown, that's all. But we are not really combining into, to get more sigmas. I think we're doing now is look at other predictions in the multi-lepton final states that were predicted and verifying whether the excesses are there or not. And now that we have more data, and hopefully in the next 1-2 years, the complete set of the run-to data will be analyzed. Because right now Atlas and CMS haven't analyzed everything in a number of very important analyses to really establish whether the 151 is real or not. And so we've moved away from just counting sigmas in the multi-lepton final states. We think that the excesses are there, they continue growing, there's no point in counting sigmas.
Fair enough. You said in response to the referee's critique, you included a model and that dropped the significance to 4 sigma. I didn't quite get that.
Right. So
global significance dropped. Yeah.
Right. So this p-value, okay. So the original p-value Okay, so the reasoning is the following. We have the multi-lepton anomalies with a lot of sigmas. And we see this excess that is predicted by the multi-lepton anomalies given the invariant mass of the two leptons. So we decided to say, look, let's just assume, let's just calculate the deviation of what we see from the background only hypothesis, okay? But okay, people want to see what happens if you use the model. What is the significance with the model, okay? Which basically no longer assumes as expectation the observation, but rather an expectation from the model. Okay, fine, we did it, and the significance goes slightly below. So, which to us, you know, still everything is significantly more significant than 3 sigma. So it doesn't really change the picture because you have the multi-lepton anomalies backing this up. And the argument is very simple, that if we had seen a bump completely serendipitously, randomly, I agree with that statement. I mean, I agree that we have to lower the significance, but this comes as something predicted by the multi-lepton anomaly. So what is the relevant question is, what is the overall significance of all these excesses, which of course is way, way more than 5 sigma. So, I mean, okay, we just have to comply with the request of the referee, but I do think that 4 sigma is not the true significance of the deviation. The true significance of the deviation from the standard model is the ensemble of this peak and the multi-lepton anomalies, which can be explained with a simplified model with way more than 5 sigma. So if we are worried about what is the level of the inability of the standard model to describe this set of excesses, is way more than 5 sigma. If you want to ask the question, what is the significance of this peak and this peak only, then yeah, it's 4 sigma, global, okay? Now, 4 sigma is a huge number. Remember, there hasn't been at the LHC a single excess in the narrow excesses ever since the Higgs discovery at the LHC, the level of even 3 sigma global. Even the 750, when you applied the Lucas-Ware effects, the significances were much more. So this is huge. I mean, even throwing away the multi-lepton anomalies, I mean, a global 4 sigma is stunning. It has never been achieved before.
Sure. And the model you said was a 2 HDM plus singlet.
Even a simpler one, just basically two scalars. That's all.
Okay.
It's okay. It's in the internal draft, so whenever it will be approved, the paper will be published. It will be updated in the archive.
No, what I just wonder is that, I mean, if it's a very simplified model, you could have, there's absolute freedom in the coupling, and you should be able to enhance the excess as much as you want. Why does it actually drop instead?
Well, basically, we go from 4.8 sigma to 4 sigma because of the model. That's all. Because the observation of the data is never equal to a model. There's always a deviation. So that's basically what explains it. But all in all, it follows the diboson signatures that we assumed in the simplified model.
Okay, very good. So this 96 GeV is also still prevailing?
Well, there's been a recent paper by Sven Maya. He's one of the people that
he's been promoting it for many years.
But look, I have my reasons why I think this may be serious. I have my reasons to believe that this may not be a fluke. But I do believe that at the LHC, the way to look for it is not as through direct production, it's through the decay of something heavy, through diboson signatures. And this explains the slight tension that Sven was always reporting between the CMS data and the LEP data. We seem to have more rate at the LHC compared to LEP. So we wrote that in the paper as well. I mean, I think this is something that needs to be pursued. In fact, what the experiment should do, which they haven't done so far, is to look for diboson signatures where you have a gap in the mass. Right now, people have focused 95 or 98% of the energies on the HH searches, which is fine, it's great. I mean, this is great job, a great work. But now you have to walk away from symmetric configurations into asymmetric configurations, something that is 150 and 96. And play with all the different combinations. And that's a new analysis. That's a new big effort. I'm not saying it comes for free, but it is now very well motivated with the emergence of the 150, the multi-lepton anomalies, and this. So I say a few years back, I was not too excited about this 96, but now I have my reasons why I think it's very reasonable to look for. It's very well substantiated to look at asymmetric configurations that also include the 96. To me, it's very well motivated. And I think it should be, the experiment should at some point, when they have person power and time to actually do it, do a proper job in asymmetric configurations.
All right. And I believe Sven has been, has explained it in the NMS system, so it should be even easier to explain it in your model with just the 2 HDM singlet, as far as I
it's work. I'm not saying it comes for free. I mean, you do have to invest time and effort to go from the HH, the symmetric search, to the asymmetric. It is work. I mean, I'm not saying it comes for free. You do have to spend some time, a couple of years maybe, understanding the background and okay, it's technically there is work entailed. I'm not saying this is something you could do with with the snap of your fingers. No, it's not. It certainly requires extra work. If you want to do a serious job in asymmetric configurations, it's something that has to be done systematically. It's not something you would do once and then let's see what happens. In particular, in the gamma BB bar, it's something that has to be exploited. I've seen results from CMS in the tau BB bar, I think, which has much less sensitivity to what we want to do, and they focus on the high masses. But I mean, it's a good start, and I believe people have now realized that they've done HH. Now it's time to move, slowly away from the symmetric distribution, the symmetric searches, into asymmetric search. So, to me, this is going to happen sooner or later, and people will get there.
Okay, good. Do we have any more questions from other participants? Okay, I guess not. So thank you very much for staying within the time allowance, Bruce. And thank you very much for a very good summary. I have, so to the participants, Bruce has already shared his slides with me. So if anybody wants to take a look after the session, please feel free to approach me or Bruce himself. So thank you very much again. And hope LHC goes and performs these analyses and we can see something very soon.
Thank you very much.
See you soon.
See you guys. Bye-bye.
See you.
Ciao, ciao.
Bye.